Hi and welcome to the Neil Ashton podcast. In each episode, we explain some of the fascinating ways that science and engineering are changing the world around us. We talk to leading engineers from elite level sports like cycling and Formula One, to some of the world's top academics to understand how fluid dynamics, machine learning, supercomputing are bringing in a new era of discovery. We also hear some of their life stories, their career advice, and lessons they've learned on the way that I hope will be helpful to you too. So sit back and enjoy this episode. Welcome back to the Neil Ashton podcast. I talked in the intro of this podcast that we would talk about things like fluid dynamics, we would talk about aerodynamics. But one of the things I also said was supercomputing and high performance computing. And I said that because nowadays, with the huge increase in using these simulation tools to simulate a car or a plane or wind turbine, or develop machine learning models like the ones that you probably use day in, day out now with large language models, you need computers to run them or to train them. And that is what is known when it's done in a very large scale and high performance way, high performance computing or supercomputing. And so I really wanted to have an episode that discuss this so people who are very familiar with this maybe got some extra details and more insights in where the future lies, or for people who are really not familiar at all, just to make you aware of this very important thing in the world around us, and that it's so important for scientific discovery. So I was very lucky that Professor Jack Dongarra was willing to speak to me, because he is arguably one of the most distinguished and famous people in the supercomputing and high performance computing world. That's because he started and really pushed this supercomputing world. He was there sort of in the early days, and is most well known for two things. One is the LINPACK, which is a software library essentially for doing linear algebra, but what it's used for is a way to benchmark systems hardware. And still today, it is one of the main benchmarks that are used to assess the top 500 list. What are the top 500 most powerful supercomputers in the world? And we talk about that in the episode. He has done many other things, but he was also one of the key contributors that developed MPI, Message-Passing-Interface. And this is a function that is used to program the majority of simulation methods like CFD, like weather modeling. But I think what he's also got to is that point where he's been so aware and been on so many advisory boards and also being a professor at Tennessee and also at Oak Ridge National Lab. He's so aware of what's going on in the world. In recent years, I found some of his papers and commentary to be incredibly insightful and very interesting. And we talked through a couple of those in the interview with him, really focusing on a couple of key topics. One, what is HPC? What is the impact of machine learning and AI on HPC? Some of the discussions around the leadership of the United States in supercomputing, which for people who are into this world is sort of a hot topic with the rise of China and other countries. We also talk about just the challenges and opportunities, what's coming next. And we finish with some more reflecting on his career and advice to people, which is, I think, always an important thing. So we didn't have a huge amount of time to discuss, and so there were many topics, and we didn't really get into his whole career and his life story, which I would love to have done, but I'm hoping you still find it an interesting discussion to listen to. So yeah, sit back and enjoy this discussion with Professor Jack Dongarra. I would start with maybe a very high level question that it seems deceptively difficult for some people to answer, which is, how would you define HPC?
So high-performance computing, what is it? High-performance computing is about using the fastest computers that we have to solve our problems, whatever problems they are. So high-performance computing uses supercomputers to help solve scientific problems, is an example. So what's a supercomputer? Supercomputers, again, would be the fastest computer that we have available to us for doing a computation. And now we have to think about what's a computation. So in this context, I would say, if we're thinking about scientific computations, we're generally talking about doing 64-bit floating point arithmetic. Sometimes it's 32-bit floating point arithmetic. With the advent of machine learning, we have hardware now that can do 16-bit floating point. They don't need as much precision in terms of the computations they're doing. And we even see the emergence of 8-bit floating point arithmetic, and maybe even less than that for some machine learning. Now, those kind of computations are hard to fit into what I would call traditional scientific computing, but there's attempts being made to do that. There's attempts being made to let's call it get an approximation to a solution in a lower precision, and then do some mathematics to improve the accuracy and come up with a solution that hopefully is as good as what you would have gotten doing 64-bit. Of course, doing 64-bit is more expensive than doing 32-bit, and 32-bit is more expensive than 16-bit, and that has to do with, in some sense, moving data and also the hardware that's inherent in the floating point units that are there. It's been said that the one who has the fastest computer can do the best science. Now, that's perhaps an overreach, but there is some truth in that. Faster computer, the supercomputers that we have are today in the what's considered exascale range. So we have two examples of those that we know about that are doing exascale computing. So exascale is defined as 10 to the 18 floating point operations per second, and that's 64-bit floating point operations. So that's a big number. 10 to the 18.
Yeah, there was two sides that I think people, or at least myself, I'm always interested of where the future lies a little bit. I want to know where things came from, but I'm also always interested to sort of to see where things are going. We've talked in some other discussions I've had with people around the pure science. So what's the future of CFD, or what's the future? But it's interesting to maybe look at that from a HPC point of view. I really enjoyed the article that you wrote, Reinventing HPC, challenges and opportunities. I know it's a difficult task to summarize that in a few minutes, but what do you kind of see as the current challenges, but the opportunities for HPC over the coming years?
Right. So let's see the challenges. Well, if we take a look at the computers that we have today, they're incredible devices, but they suffer from the standpoint of moving data. So data movement is the most expensive thing that we do on a computer today. So moving data from one part of the machine to another part of the machine where it's going to be used is very expensive. So it's much more expensive than doing floating point operations. And floating point operations today on our computers are really over-provisioned, I feel. So we have too much floating point capacity, and we have a hard time effectively using the floating point units because of passing data to them. So we spend most of the time passing data. So the challenge would be to design a system that that can overcome some of that resistance in passing data. Our computers today, our supercomputers today, are purchased or acquired in a sort of a strange way. So what we do is we say we have a desire to have a machine at this level of performance, and we have this much money. So then we tell the vendors we need a machine that matches that performance with this cap on it. So I'm being very crude in terms of the parameters here, but it's sort of like this. And then a vendor goes off and cobbles together a machine, usually out of commodity parts, and bids that machine. And if they win the bid, and there's a lot of things that go into winning a bid and making things work. then they put together a machine, and it basically gets thrown over the fence. And we, on the other side of that fence, the people who are intended to use that computer, sort of scramble for the next 3 or 4 years to figure out how to use it effectively. And that scrambling, is an incredibly intensive process of optimizing, redoing algorithms, redesigning algorithms, creating new algorithms that can effectively function in the parameters of that new machine. So we're doing, in some sense, we're doing that incorrectly. So we're not designing a machine that's suited for the scientific problems that we have. We're designing a machine based on how much money we have and what the expected performance could be in terms of peak performance of all things. So we end up with a computer that, for some outdated benchmark, perhaps can reach the highest levels we asked for, but for realistic problems, we run much less than that. And the example that I usually drag out is something perhaps I'm responsible for, is the LINPACK benchmark. So LINPACK benchmark is solving a dense system of linear equations using a standard algorithm. It's the algorithm's Gauss elimination with partial pivoting. It's the algorithm I learned when I was in high school for solving a system of linear equations. And the benchmark is to use that algorithm to solve a dense matrix problem and to look at the performance with 64-bit accuracy. So, that problem is at its core doing a matrix multiply. So if your hardware can do matrix multiply well, that algorithm is going to run very well. Now, that algorithm is not very relevant to today's scientific computations. That is to say, the computations we do on supercomputers, they usually don't look like matrix multiply. They look like something with a sparse data structure. So it's solving the same problem, by the way. So solving this LINPACK benchmark solves a system of linear equations, AX equals B. So you're given A and you're given B and you're asked to compute X, and you're told to use Gauss elimination with partial pivoting, and that matrix A is dense. So all the elements are filled in with non-zero components, and you're asked to use that algorithm. We have another benchmark that's called the High Performance Conjugate Gradients benchmark, HPCG. And that benchmark, again, solves that same problem, AX equals B, but the data structures are different for the matrix A. The data is sparse. So we have a sparse matrix representation for the problem. And that sparse matrix is similar, the way in which it's formed is similar to what we typically use supercomputers to do. And that's solve a three-dimensional partial differential equation. So when we discretize that differential equation, we end up with a matrix problem. That matrix problem is sparse, and we use an iterative method to solve it. So it's not solved in the sense that we solved that dense problem. It's using a different approach to solving it, and that approach does not have matrix multiply at its core. It has a sparse matrix vector product, which requires you to move data, and it gets very little reuse of the data. So the data is basically passed into the functional units, computations done, and then there's no reuse of that data, and you have to do it again for the next iteration. And just in terms of raw numbers, the dense matrix problem, we can get probably 70 to 80% of the theoretical peak performance in 64-bit precision. For the sparse problem, unfortunately, we get less than 3% of the theoretical peak performance. So problems that we are intending to solve on these supercomputers, we're ending up with 3% of efficiency, let's call it. And is that a good or a bad thing? Well, I would say that's not a very good use of the resources that we have. And why is that the case? Why do we only get 3%? It's because we don't have a good way to pass data around. And we've cobbled together a machine based on commodity parts, commodity CPUs, commodity GPUs, commodity interconnects, commodity memory, and all of that comes together to give us a machine with a very high theoretical peak performance, but very inefficient in terms of how it's used.
How much, I guess you're alluding to there of one of the conclusions around co-design. Are you essentially saying that really the hardware and the software should be more tightly sort of coupled together rather than there being how can that be addressed, I suppose, pragmatically or practically?
Right. So we had a mantra with some of the Department of Energy projects and the mantra was to do co-design. What is co-design? Well, it's to get the hardware people together with the computational scientists, together with the guys designing algorithms that'll solve those computational problems, along with the software people that are going to write software for doing those algorithms. So it gets the architects together with the scientists, together with the computer people who are doing things, and they're going to co-design a machine based on the aspects of the applications that they have, how to make those applications run as efficiently as possible on some architecture, and working with the architects, come up with a piece of hardware that can satisfy that problem. So that's the mantra. In the end, what we got is somebody throwing a machine over the fence, and the computational people scramble for the next 3 years trying to figure out how to use it. And there is no real co-design of that machine. So again, we're stuck using commodity processors. We've lost, in some sense, I can remember back when I was in school, there were many universities doing architectural work in terms of building experimental machines that potentially could solve challenging problems. And I think we've lost some of that. So we've lost some of the ability to do that fundamental research in terms of designing architectures that would meet the needs of the computational science community. So maybe we should go back and invest, I'll say, in that effort. That is, invest in terms of allowing those universities to do architectural research that would benefit scientific computing. Architectural research is being done, of course, in universities, but with the focus being on scientific computing, I think is the thing that we've lost.
Do you think that AI and machine learning has been a force for good for HPC in the sense that it's obviously a user of HPC and has driven huge new investment, or has it been negative because it's sort of diverted that from computational science towards a different discipline that maybe doesn't suit it?
So I would say AIs and machine learning are causing a revolution to take place in how we look at scientific problems. Almost every scientific application that I see today is embedding machine learning and artificial intelligence in it. And it's having a very positive effect in terms of allowing those applications to get a better solution, better time to solution, a more accurate solution. And I'm not saying that they replace the traditional classical approaches. What they do is they augment them. They're a tool that's being used now by the computational scientists. So it's a tremendous positive influence in terms of how we solve problems, and that's going to be a great benefit as we go forward and really understand how we can use the technology and use it as a tool to solve our problems much better than we're doing today. So it's really it's a thing which will help us amplify our ability to solve these problems.
But do you I'm apologies if I'm wrong on this one, but is there therefore a logic that some of the methods to evaluate the top 500 should be more skewed to include machine learning, given that increasingly a lot of these supercomputers will run more and more machine learning workloads with different algorithms and methods?
So I guess as a person who has developed accidentally benchmarks that have gotten take up in the community, I'll say that we should have a lot of benchmarks. We shouldn't just have one or two benchmarks. We should have a bunch of benchmarks. The benchmark should reflect the applications that we're going to use these machines for. So having many benchmarks allows us maybe to dial up these benchmarks to get a handle on what our application will look like when run on these machines. So we should, of course, keep the existing benchmarks. There's a lot of historical information, trends, and other things that we get out of them. So it's been very informative and has been beneficial. So I would advocate keeping them, not throwing them away, but I would say we should augment them. And we've tried to do that. I've tried to do that just as I go through trying to understand how effectively to use the machines. So HPL was something that was done, to be honest, it was done in the late 70s. So we've got something that has, almost a 50-year horizon here. And the top 500 has been around 30 plus years. So that's a historical snapshot of that information in some sense for high performance computing. And now we have this HPCG benchmark, which is, again, looking at something a little bit different, but more relevant perhaps to the applications that we do. And, there are other machine learning benchmarks that I think need to be understood and explored. But, with these benchmarks, we want to keep them around for a long period. We want to make sure they reflect really what's going on in the applications and what we can expect. So some of that is unknown territory today. So I would say, we're in a learning process, and it'll take some time for the right benchmarks to perhaps to emerge. But I think we should be working towards a whole suite of benchmarks that can be used to evaluate a system rather than just focusing on one. We've tried to address that in my group. We tried to address that by tweaking, I'll say, the HPL benchmark. So the benchmark that does a dense matrix computation. Tweak it in the sense that we're trying to understand what we can get out of using mixed precision. So the mixed precision is can we get by with a low precision start to the problem and then do some mathematics to improve the solution to the same that we would have gotten had we done everything in 64-bit. So there's a benchmark that goes by the name of HPL MXP. MXP is for mixed precision. So it allows the use of 16-bit and 32-bit arithmetic. It has a problem, a dense matrix problem that you're asked to solve. And there's a technique that we have as a reference implementation, which uses a iteration. It constructs a approximate solution in lower precision and then uses an iterative technique on that dense matrix problem to converge to a much higher accuracy result. And we can show, very efficient speed ups over time based on that. And that's one of the benchmarks that the guys at Argonne and also at Oak Ridge ran, and a bunch of other places have run to show significant speed ups. So there's a need for many benchmarks, and those benchmarks should reflect the applications that we're going to be using on the machines.
But that's an interesting point about the precision, because that was kind of my question before a little bit in terms of the positivity, the negativity, the direction with machine learning, in a sense, for many computational things, mixed precision or double seems to be what's required. But it's good, obviously, that we've been worked to see if there's a way around it. But obviously, a lot of machine learning methods can get huge speed ups from using lower precision. And there's a lot of money in that for the chip vendors and the hyperscalers. So I guess, is there a need to sort of not get overhyped by machine learning? In the sense, you still have to remember that there are some things that require one chip cannot solve it all, I guess. Is that the right way? Or...
Well, I'm thankful that NVIDIA still does 64-bit arithmetic in their
Yes.
accelerators. So
Yeah.
that's the first thing. Thank you very much for keeping that real estate there, as opposed to selling out totally and just doing 16-bit arithmetic, which is what machine learning needs to do its problem. So yeah, I think that there's room there to, and I think we're trying to understand how we can push the precision, the accuracy, and what we can do to enhance the accuracy once we've gotten a result. And that's current research. So there's a lot of activity there. There's a cottage industry, I'll call it, trying to use mixed precision to solve scientific problems, trying to exploit that 16-bit arithmetic as much as possible, and I've seen some reasonable results from that. So I would say that's a positive thing to exploit. Again, I'm thankful that we have 64-bit. And I saw a paper recently which was quite interesting. They were using integer arithmetic. So the NVIDIA GPUs have the ability to do fixed point arithmetic very fast. So it's much faster than floating point, 16-bit fixed point arithmetic, which gets you a 32-bit result, fixed point integer arithmetic, and that's being used to actually implement the procedure for doing floating point matrix multiply. So they essentially think of you have two matrices you want to multiply together, and the algorithm basically separates the numbers and bins them in a certain way so that they can do fixed point arithmetic on those bins of numbers, and then upscale that to floating point and get a floating point result as a result of that very efficiently. And it can be encapsulated so that the user doesn't even know that's happening. So it's under the covers. They basically do a matrix multiply, and they're expecting a 64-bit result. And under the covers, it's being done in integer arithmetic with the correct precision, with the correct ability to detect errors in it, with all the floating point things we would like to see from IEEE arithmetic. In the end, they get a result which is done much faster, but using that integer unit. There are some hiccups along the way, but that's a very interesting approach to dealing with the situation of the hardware providing a capability and exploiting that hardware capability to get results that can be used.
Two questions for you. One, is it really necessary in the current age to have a single system with 50,000 GPUs or 100,000 GPUs? Does anybody actually use the full system? Or is it actually more economical or more effective to have multiple systems, whether it's a cloud or not, because nobody runs on the full system anyway? Or is there a bigger picture of politics and needing to hit numbers? I'd be interested to get your take on the sort of the need for just one massive machine.
Right. So the question is, should I build one exascale machine or get 1,000 petascale machines? That's the equivalent of that question, perhaps. Yeah. So let me say that the Department of Energy is investing in exascale computing, and they've put together a program called the Exascale Computing Program, the ECP, along with the Exascale Computing Initiative, and it's a program that was over 7 years, and it was designed to produce those exascale computers. So they get 3 exascale computers. The price tag is $600 million for each one of those, and the whole program is $4 billion. So $4 billion over 7 years to get to exascale. That clock was set a little over 7 years ago. The program has run its course. It spent those $4 billion, and we have 3 exascale machines. One is at Oak Ridge National Lab called Frontier. Another is at Argonne National Laboratory. That's called Aurora. And the third one is a machine that's being constructed today at Lawrence Livermore National Lab called El Capitan. So those are hardware machines that all have exascale plus capabilities. And the purpose of those machines are to solve some very challenging problems. So the Department of Energy in this program defined, I think it was 21 or 24 applications that they were going to target to use the exascale machine. And in the course of solving those problems, not solving them, but using those exascale machines to push the boundaries for those problems forward, it's intended for those exascale machines to be used at some point during the course of its life, to be used, the whole machine to be used to solve or to be used in the solution for some aspects of those 21 problems. So yes, those machines are intended to be used at their full scale to solve one problem, to help solve that one problem. And when it's not being used to solve that one problem, of course, it's being used to solve many problems simultaneously through a time-shared, through a system of using that machine. And so that says there is a need for the exascale machine. We couldn't get by with 1,000 petascale machines to solve those very challenging problems, which have been designated as challenging problems. The other part of your question, I think, is something that I feel very envious about. So the hyperscalers can go off and build a machine which is co-designed. It is co-designed. Here's the problem that we want to solve. We're going to build hardware to help us solve that problem. And they build hardware to do that. So you go down the list. Amazon has their own hardware. Microsoft has their hardware. Google has their hardware. So they've invested in that. They have enough resources that they can do that. So, the statement that we make, I think, in one of the papers is the hyperscalers, they have resources. They have tremendous amount of resources, so they're exothermic. They can do that investment in terms of building hardware to help them solve the specific problems that they have. Where in the high performance computing scientific domain, which is the research side with DOE, NSF, we're endothermic. We don't have enough resources to solve our problems, and that leads us down that path, which says we're going to cobble together a machine based on commodity parts that are available, and hopefully get something that can be used to help us solve our high-performance computing problems. And the machine is not co-designed in the sense that the hyperscalers go off and co-design a machine with very specific requirements to solve the kind of problem that they have. So again, I'm envious that we can't do that in the high-performance computing. I think we should invest in terms of allowing research to take place so that we can investigate what architectures would be the right.
Is the US still the leader in HPC? I find it very interesting, the analysis. I will put a copy of it in the comments of this thing. But you were the I think the main author, along with some collaborators who define this. I think you know what I'm talking about. It'd be interesting to get your perspective on that and what should be done to address.
Right. So I was part of a Department of Energy study that was done for the Office of Science on U.S. competitiveness in this area. So there's a number of issues there, some of which we've touched on. But the elephant in the room is, does the U.S. have the same or greater capabilities than China in terms of high performance computing? So I think we can say that Europe is developing high performance computing. They have a lot of programs in place. They're European centric in some sense. They want to use RISC-V. They have ARM processors that they're looking at. They have a number of things that are based on things which are more things that would benefit the European Commission, the European Union, and I think that's fine. That's a great thing, and we'll learn a little bit from what they're will learn from what they're doing. So that's a good thing. Japan, has their own hardware that they've developed, very impressive systems. The Fugaku system is their top tier machine, which has very, very strong capabilities. It's one of the machines in the top 10 that are not using GPUs. So they have vector architecture at their disposal, and they're using an ARM processor. They've augmented it with vector instructions, but their secret sauce is their interconnect network is very efficient. And it's through that efficiency that they can get very good performance. And they come out, on tops for things that matter in terms of data movement. The other one is China. China is interesting. They've developed, they have been forced into developing their own hardware. So that the forcing was the U.S. putting sanctions on technology going to China. So it was initially processors, then GPUs, and now the ability to use TSMC for fabrication is taken out of their hands. So China, perhaps in a reaction to that, has stopped submitting benchmark numbers for the top 500. So we see no new machines coming out of the China that are no new entries coming from submitting numbers to the top 500. So that's that's a bit they're taking a very strong stance, I would say, on that. And what's the reason for that? Well, they're afraid the U.S. will take more action, is the only thing I can think of. So again, it's a situation where they're reacting in that way. And again, China's pivoted, and they're designing their own hardware for their high performance machines. They have their own chips that they're designing. Question is, where are those chips fabricated? I would guess they're fabricated in Taiwan, but they have fabrication facilities in China now, which are a little bit below what one can do at TSMC, and those chips will probably be fabricated there for the next generation of hardware that they're producing. So it's unfortunate that they've shut the window, so we can't really see what's going on. Occasionally they write a scientific paper which describes the hardware, so we get a glimpse of what that hardware looks like, but we don't have a real good benchmark associated with it. We can't see how well it does provide. So that's a bit unfortunate, but that's life. We have this thing called the Gordon Bell Prize. So Gordon Bell passed away just recently. Gordon set up this prize that would set up a competition to see who can improve on real applications using high performance computing, is sort of the short version of what the prize is about. And it's competed, and people submit a paper that describes the application and the results that they got on their supercomputer. And we're now looking at the current entries that are being submitted. So I'm one of the judges who are looking at the entries there, and China's submitting results for applications that they're running on their current generation of supercomputers. Those supercomputers are described in the machine to some extent, and we could see the performance that they're getting on those applications, not on the standard benchmark where we have perhaps equal understanding of what was done and how it was done. So they're making progress. They have high performance machines. The U.S. is certainly competitive to some extent. There's claims that the Chinese machines are faster for some of these benchmarks. That may be the case, but the China is competitive though with what we see from the U.S. systems.
And if you fast forward, you mentioned before about the X-Scale project, it was a 7-year project to sort of reach these frontier, El Capitan, etc. If you were to fast forward 7 years from now, is there the investment in place to make an equal leap, or is it the scenario that we won't make the same progression that we've made, and other countries that have doubled down will make a bigger gain?
Right. So one has to make an investment to get the advances in hardware applications, algorithms, and software. The ECP project was a wonderful project. It was 7 years of long-term funding. It involved 800 people working on high-performance computing, from applications, from software, from algorithms. All received funding to advance things, to further, as well as the hardware being purchased. So half the money went for hardware, and the other half went for algorithms and software and applications. So that was an interesting split of that funding. But it ended. The project ended, and the sad part about that is there's no follow-on project. So we had 800 people working on this effort, and it ended. It ended in December of last year, and those 800 people are scrambling for jobs. So we have very highly trained people who understand high-performance computing at various levels, who are now maybe out of a job, and so they're scrambling still to find its way. So I think it's a sad day for the Department of Energy, who invested in the algorithm software applications as well as the hardware, and now those people who designed those algorithms, applications, and software may be looking for a job. And I know that many of the people are being sucked up by the hyperscalers or by companies like NVIDIA to develop their technology. So that's a loss, I would say, for the community, and that loss is hard to replace. You can't just spin that up overnight. If you wanted to restart a program, you can't restart the program. So it's a situation where we would have to follow on. And there's an attempt to follow on with AI for science, and that process is undergoing and getting off the ground now. But it wasn't a clear follow-on. It wasn't something that was dovetailed into by the shutdown of the ECP project. So I think it's important. I think the investment needs to be made. We need to have people who can guarantee a job long-term. The talents that they bring with them are hard to replace if they go away, and we're seeing some of that drain today in going to the hyperscaler companies. I feel DOE shouldn't be a minor league team for the hyperscaler guys. They should be the major leagues as well. The people should be funded for doing that in the long term.
Yeah. One question, I guess, still on the future, peering into the future a little bit, is obviously, depending on where you are in the computer science or HPC world, either you're very full on with GPUs and you've known about it for decades like yourself, or it still seems quite new. But that, I guess, will come to an end, as in the sense of the acceleration, the performance improvement, the new. Are there any technologies that you see coming that would, just as GPUs has arguably given a big boost from the traditional x86 CPU, do you see a new technology around the horizon that people should be sort of reading up about or being more aware of than they currently are?
Right. So if we look back and look at where we've been, we had machines which were special purpose machines for doing scientific computing. You go look at companies like Cray, CDC, Hitachi, Fujitsu, built machines which were specific for that, but the market couldn't sustain them. And we had microprocessors come up and be more powerful. So we had special purpose machines, vector computers. Then we had multi-core computers, which was the architecture that led to the downfall of those vector-based systems, the attack of the killer micros. And then we had parallel computing come into place. And then we had GPUs. I'm oversimplifying this, but that's sort of the progression that we had in terms of getting to the point where we are now. So what's next is your question. And, my crystal ball isn't that good to predict what's the next big thing. But, machine learning comes into it. It's a tool that we're going to use to help us solve the problems, but it's not architectural advancement that we have. We think about what are the changes in the architecture that we might envision. We can see things like neuromorphic computing. We see things like optical computing. We see things like we see things like potentially way in the future quantum-based computing. Those are all things which could make perhaps make improvements where we get that leap, which we've had in the past with those generations of things. So, but quantum computing is way off into the future, is my feeling. A lot of so it's an important topic. We should invest in research into it. It's something which has promise, of course, but it's not going to replace our existing machines in the near term, or not in my lifetime. So it's something which needs to be worked on and figured out how we can effectively use them. And it's not going to be the thing that replaces our high performance machines. It's going to be something that we add to the ensemble that we use to attack problems. So again, we have CPUs and GPUs and optical and neuromorphic and DNA-based stuff maybe, and adding quantum to that mix is something that perhaps can happen, and that would then lead to problems that could use those devices, perhaps getting a boost in terms of how they solve their problems.
I did want to change track a little bit, because you've had an amazing career. Obviously, you were very modest when you mentioned about, I was kind of involved a little bit with some benchmarking, obviously with LINPACK and MPI and many other things that you contributed to. I know it's a difficult question to ask, but do you have any standout sort of memorable things from your career that were sort of even just a day or a moment standing on a stage or is there anything that, you sit when you are having a drink and you sort of think about what you've been doing? Is there anything that stands out?
So that's a hard question to answer. So I like to think I've contributed to three things. And one thing is developing software and algorithms for solving some standard problems in linear algebra. So that's something I think I've contributed to. And along with that goes portability and performance. And the second thing is tools for doing distributed computing. So there I put in the basket, MPI. So I wasn't solely around to do MPI. There was a group of people, of course, who contributed to the standard, but we were all there together at ground zero. And the third thing is about performance evaluation. And there again, it's an accident in some sense. So the way I think of this is my true passion is with linear algebra and developing software that is portable and can be run efficiently. So that's the goal. And along the way, we needed tools to make that happen. So we needed tools to do the evaluation. So that's where the benchmarking comes in. So we developed tools which exposed how well that software would run on these systems. And then we needed, as the architectures changed, went from sequential to vector to parallel, we needed some way to engage with parallel processing. When we started doing MPI, it was the Wild West in terms of message passing. Each vendor had their own way of doing it. And there was a community that recognized we needed to standardize it. And it wasn't going to happen by the vendors. It was going to happen in an organic way from the ground up. And we formed a de facto committee to look at what would we need in terms of mechanisms for doing message passing on those systems that could be portable and efficient. And out of that came MPI. So those are sort of the mixes. So if I was saying my contribution, what did I feel most proud about? It must be the linear algebra software, and then these benchmarking things, and the message passing stuff comes along as a necessity to doing that linear algebra stuff.
What about, I don't want to say regrets, but are there anything I really wish I'd done that, or I missed that opportunity, or, is there anything where you look back and you wish you'd done?
Wish I'd done. So I don't have regrets in that context. I mean, everything, I have to say, people come up and ask me, I want to do what you did. How did you do it? And I say, well, it was serendipitous. I can't give you a formula for it. I wanted to be a high school science teacher. So that was my ambition when I started. And then the things changed along the way, and I can't reproduce those changes. It just happened. I happened to be chosen to work at Argonne National Lab, spend a semester with a scientist. And, that was transformational in terms of looking at or follow, it really opened my eyes, and I saw passion for doing these things. I changed the course of what I wanted to do based on that. And I think I was in the right place at the right time for many of the events that have occurred. So it's hard to replicate that. I tell people, in research, we should expect to fail. So that's an important lesson that everybody in research should, going into research, should understand. It's a process where I don't know the solution ahead of time. I can't give you what it's going to be, but I'm going to try things, and through that experimental process, I may hit on something which is going to lead to the right thing. So, expect to fail if you're going to do research. Follow your passion, do something that you feel passionate about, and take that forward. You should, networking is an important thing. Talking to other people, interacting with people, trying to, in solving a problem, we often need some other stimulus, and talking to people is a good way to get that. Throw something up against the wall and let other people see it, and how they react is going to be important. And I guess the other thing is, aim high. Try to solve challenging problems. Try to solve problems which are stretching what you can do and what others have tried to do. So it again gives you an opportunity to advance the field and to do that. So those are my recommendations. I tell my students. There's four
And
things.
are you optimistic about the future of HPC and scientific computing?
Oh, absolutely. Yeah, this is a great time. So, and it's been a great time for a while. So it continues to be a great time, I guess I should say. And it's a great time because of all of the things that are happening in the field, in high performance computing, and AI is part of that. Machine learning is certainly there. Looking for the next big advance in terms of architectural features. That's an important thing. From my standpoint, how can I bring all this mathematical knowledge that's been accumulated over time in solving the next set of problems on the current, on the next, the problems that we have on the next generation of architectures. So that requires innovation, and some of that innovation comes about because of not creating something, but using something that people have created in the past and bringing it forward to be used on today's environment.
Well, thank you. I know that you're a very busy person, so I want to be respectful of your time, but I really appreciate you coming to speak. I think you very eloquently are. They always say, someone told me that you're a true expert when you can explain things simply. And what I really like is that anytime I ask you a question, I love how you simplified it in such a way, and that's a real sign of expertise. So, and a university professor, clearly. So, thank you very much. And
well, thank you for that compliment. It was fun to talk to you, and I look forward to seeing what you produce.
All right, cheers.